For this lesson, we're going to be talking about permutations. So we're going to start with a little bit of a warm-up, and then we'll continue into some more challenging examples, as well as the actual formula for our permutations. So to start, a data management class has developed a survey which has 9 questions. 2 of these questions are loaded questions. To start, how many ways can the questions be arranged? So we'll start by drawing out some lines to represent our questions. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 questions. So when we go to pick that first question, we have all 9 questions to choose from. Then for question 2, because we've already used one up, we only have 8 questions to choose from. Then we would have 7 questions to choose from, 6, 5, 4, 3, 2, 1. Now, because we require question 1 and question 2 and question 3, we multiply here. And this will give us 9 factorial, which is 362,880. So that is our total ways to rearrange these 9 questions if there are no restrictions on their order. Now, let's add in some restrictions. Now, if the 2 loaded questions must come one after the other, how many possible arrangements are there for the survey? So again, I'm going to set up all 9 spots. But this time our 2 loaded questions have to be together. So we'll put our first loaded question here, only one way to do that, and our second loaded question here, only one way to do that. Now, because I've already used up the 2 loaded questions, for the third spot, we only have the other 7 to choose from. Then for the fourth spot, we would only have 6 to choose from, then 5, then 4, then 3, then 2, then 1. Again, because I require question 1 and question 2 and question 3 and question 4, etc., I multiply, and that will equal 7 factorial. Now, I don't have to have the loaded questions right at the beginning. I could have them together in different spots. So these 2 loaded questions could be here, or they could be here, or they could be here, or here, or here, or here, or here, or here. And we have 8 different spots for those loaded questions. So to account for that, I multiply by 8. Then I don't have to have loaded question 1 and then loaded question 2. I could have 2 then 1 or 1 then 2. Because of that, I have to multiply by 2 because we could have L1, L2 or L2, L1. Then I put all of that into my calculator. 7 factorial multiplied by 8 multiplied by 2 is 80,640 arrangements. Now for C, if our 2 loaded questions are to be separated by at least one other question, how many arrangements are there for the survey? So in other words, how many ways can we have our survey so that the loaded questions are not together? Now there's lots of ways we could have them not together. They could be separated by 1 question, 2 questions, 3 questions, 4 questions, way too many to count. So it's a little bit easier for us to take our total ways and then subtract the ones we don't want. So the total ways we could arrange our survey, there were 362,880. And then we'll subtract the ones we don't want, which are the ones where our loaded questions are together. So that would be 80,640. Put that into my calculator, and I get 282,240 ways. There we go. Now for our next one, this one's slightly different. A teacher has a bank of 38 questions for a particular test. 10 questions are to be chosen randomly from the question bank. How many different looking tests can be made? So from this bank of 38 questions, we're only choosing 10. So each time we go to make this test, we randomly select 10 of them. So let's write out all of our spaces for the 10 questions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we have a question bank that is 38 questions. So for question 1, there are 38 different choices. I could select any of those 38 questions. So here, 38 choices. Now for question 2, I've already picked the first question. So now I only have 37 options. Then for the third question, I'd only have 36, 35, 34, 33, 32, 31, 30, 29. Because I will require question 1 and question 2 and question 3, etc., I multiply. And if I put all of this in my calculator, I will get a really big number. We have 1.72 times 10 to the 15 ways. And this makes sense that it's so big if you think about how many options we would have for this test or how many different ones could be made if I was randomly selecting 10 out of 38, loads and loads of options. So it makes sense that this number is really, really big. Now, sometimes we can't really write out these spaces. Writing out these spaces doesn't always work. If we're looking at some really big numbers, sometimes this process that we've been doing isn't efficient. So we have some alternatives and some different ways that we can approach this. And that's where we start talking about permutations. So a permutation is when an arrangement is made in a definite order. In other words, order is really important here. So for example, we were looking at the order of questions on a test. If I rearranged those questions, that's a different version of the test. The order matters. If questions are switched around, that's a different arrangement. The order in which I pick them, question 1, question 2, question 3, question 4, impacts whether we have version A, version B, version C. That's how I know order matters. If I'm trying to determine how many arrangements I have and order does matter, that's when I'm looking at a permutation. Now, the total number of our possible arrangements, when order matters, can be computed using this formula here. We denote it as NPR, and this is the button you'll be looking for on your calculator. So really make sure you know how to find this because it's a very, very useful button. Now, in this notation, N is our number of distinct items. In other words, we had a question bank of 39 questions, and R is the number of places in the arrangement. We're choosing 10 of these questions. Now, there's a button on your calculator, but sometimes you will be asked to do it by hand because that is a curriculum expectation. So this is our formula to do it by hand here. N permute R, that's how we say that, equals N factorial divided by N minus R factorial. So once you determine N and R, the formula is very, very straightforward. So let's try a couple of examples here. So for this first example, we have 10 students to choose from and 3 different chairs. How many ways are there to arrange 3 of the 10 students in the chairs? Firstly, we want to determine, does order matter here? Is this a permutation? So if we have student A sitting in chair 1, student B, then student C, that is absolutely a different arrangement, then student C, student B, student A, right? Those are two different things. Therefore, order does matter, and this is a permutation. So we'll start by using our fundamental multiplicative counting principle, which we were using prior to finding out this formula. So when we're looking at the fundamental multiplicative counting principle, that's where we draw out our spaces. So we have 3 chairs, first chair, second chair, and our third chair. Now we have 10 students to choose from. So we have 10 students to choose from for the first chair, 9 students to choose from for the second chair, and 8 students to choose from for the third chair. Now, because I require a student in chair 1 and chair 2 and chair 3, I multiply, and that will give us 720 ways. Now, let's try using our permutations formula instead. So n is our number of distinct items. In this case, we're looking at students. We have 10 students to choose from. So n is 10. Now, how many of those students are we choosing? We are choosing 3 of them because we only have 3 chairs. So we're going to do 10 permute 3, and we'll fill in the formula. So n is 10 divided by n minus r factorial. And then we just put this into our formula. So simplify it. Now we can simplify this totally by hand. So we'll have 10, we'll multiply and expand the numerator, keep our denominator. Our 7 factorials cancel, and we're left with 720. So you can see here how it ends up working out to be the exact same thing. And this one's nice because we can look at both options, but sometimes our numbers are just too big to really work with our fundamental counting principle. All right, let's try another example. So here, a brand new high school math council is being formed. 7 people from data management class A have volunteered, and 6 people from another data management class, we'll call that class B, have also volunteered to join. The math council is to have an executive that includes the positions of president, vice president, secretary, treasurer, and spirit coordinator. Our first question asks, how many different executives can be made from the volunteers of both data management classes? So let's first think about how many students we have. How many are we working with? So our total number of people will be, we have 6 people from class B and 7 from class A. So we have 13 students total. Now, how many positions do we have? We have president, vice president, secretary, treasurer, and spirit coordinator. Now, because we have 13 students, we have 13 choices for president, then we would have 12 choices for vice president, 11 choices for secretary, 10 for treasurer, and 9 for spirit coordinator. Now, because we require a president and a vice president and a secretary and a treasurer and a spirit coordinator, we multiply, and this gives us 154,440. That's using our fundamental counting principle, but we could have also used permutations, 13 permute 5. If you use the formula or put this into your calculator, we get the exact same answer. So it really doesn't matter which way you do it. Whatever you're most comfortable with works perfectly fine, unless, of course, the question specifies a specific way to do it. Now, let's add on some conditions. Let's add on another layer to this to make it a little bit more challenging. How many different executives can be made if the president and secretary must come from class A and the other positions must come from class B? So we're still going to set up our lines and our spaces. So from Class A, we need our president and our secretary. These ones must come from Class A. And then from Class B, we need our vice president, our treasurer, and our spirit coordinator coming from Class B. So from Class A, we have 7 students in Class A. So 7 choices for president, which leaves 6 choices for secretary. Similarly, in Class B, we have 6 students total. So 6 options for the vice president, 5 for treasurer, 4 for the spirit coordinator. And because, again, we require a president and a secretary and a vice president and a treasurer, we multiply. There we go. And this will give us 5,040. Now we can also do this with permutations. For Class A, we had 7 people and we needed 2, so 7 permute 2. And from Class B, we had 6 people and we chose 3. So we do 6 permute 3. Multiply that, we get the same thing. There we go. Now our final example here, how many different executives can be made if the president must come from Class A, while the vice president and secretary must come from Class B, and then the other positions can be filled by any student, no restrictions there. Again, let's draw out all of the spaces. So from Class A, we need the president. From Class B, we need the VP and the secretary. And then from anyone left over, we need the other 2 positions, treasurer and spirit coordinator. So for Class A, there were 7 students to choose from, so we have 7 options for the president. Then for Class B, we have 6 people to choose from, so 6, and that would give us 5 students left to choose for the secretary position. Now for the other 2. Now that we've picked these ones, it doesn't matter what class they come from. So we had 13 students total, 3 have already been assigned roles, so we have 10 left to choose from for treasurer, and then 9 left for our spirit coordinator. Then we require a president and a vice president and a secretary and a treasurer and a spirit coordinator, so that will give us 18,900. Again, we could have also used our permutation formula. So we would have 7 permute 1 because there was only 1 position. We would then have 6 permute 2 because there were 2 positions. And finally, we will have 10 permute 2 because there were 10 students left and 2 positions. Then we have 18,900. And that's our final answer.